All right. So we're in section 13.4, and we're going to talk about differentials. So if we remember back, it was probably quite a while ago. When we learned single variable calculus, we talked about differentials for a single variable function, and we said that dy, our differential, was f prime of x dx, and we could use that as a linear approximation. So if we draw a quick sketch here about what we're talking about in the plane, we have a curve in the plane. And so here's our curve, some curve like so, and then we approximate that curve with the tangent line at a point. So we'll draw our tangent line there. And we approximated the change in the function from this point to this point by the change in the tangent line, because lines are a little easier to deal with. So I'm just going to project this down like so, and this was delta x, our increment of x, which we said that we could represent that here as dx. So this is not an infinitesimal, this is a increment, and this change was our differential, and the change in the function itself was delta y. So our differential was this change in the height of the change in the y value of the tangent line. So we're going to do the same thing, apply that same concept to a multivariable function. We're going to call delta x, so small change in x, and delta y, and we're going to say for z equals f of x, y. So we're talking about a multivariable function now. So this is what we did in single variable calculus for our differential. So if we have a multivariable function, we're going to say delta x and delta y, these are increments. These are increments. So we're not necessarily talking about infinitesimals, we're just talking about a change. The increment of our function is, we're going to say delta z is f of x plus delta x, comma y plus delta y, minus f of xy. So we're talking the exact same thing that we're talking here. This change in the function. So let's make a little sketch, a three-dimensional sketch. So our coordinate system down here. And we have a surface up here above the xy plane, some kind of surface. There's our generic surface. And we have a curve on this surface. So delta z is the change in the z value between these 2 points. So if I project this over, like so, project this over, this is our delta z, and we're moving from some point here. To some point here. So this is the point xy, and then we move to x plus delta x, comma, y plus delta y. And delta x and delta y are the change in the x value and the change in the y value from one point to the other. So this is the increment we're talking about. So delta z tells us how much the function changes as we move from the one point to the other. We're going to define the differential of the function to be the change in the height of the tangent plane. Just like we talked about the differential here being the change in the height of the tangent line, we're going to define the differential to be the change in the height of the tangent plane. We're going to use that as an approximation. So we're going to define this differential as we move from the one point to the other. We can show that this differential, this change in height of the tangent plane, dz, we're going to say that dz is our differential, is dz dx delta x plus dz dy delta y. So dz dx delta x is exactly like the single variable differential that we talked about here. dz dx gives us the change in the height of the tangent plane due to moving from x to x plus delta x, so moving in the x direction. And this portion gives us the change in height of the tangent plane as we move from y to y plus delta y, so we're in the y direction. So this is a contribution to the change in height as we move in the x direction. This is the contribution as we change in height in the y direction. So what we're talking about here, if we draw another picture, just to get a visual of what we mean. So here's our coordinate system, z. Make sure I can fit all this in my drawing. So here's my surface. There's my surface, and I'm going to draw in my tangent plane here. I'll draw my tangent plane in a dotted red. So my tangent plane at this point, that's my tangent plane at xy. So this is the three-dimensional version of the picture we drew back here of this picture. So this is our tangent plane. We're saying dz is now the differential is how much the tangent plane changes from xy, from this point xy to x plus delta x and y plus delta y. So we move between these 2 points, the tangent plane, and then delta z would be the change in height of the surface in that same interval that we're changing from x y to x plus delta x y plus delta y. So this is just a three-dimensional version of the picture that we drew before. If we turn this sideways, so we were looking exactly sideways at the plane, we would get this picture that looks something like this, where the red line is our surface, and this would be our tangent plane looking at it exactly sideways. So this is what we're talking about. This is our differential. We usually write this dz equals dz dx dx plus dz dy dy. And we're not saying that dx and dy are infinitesimals. These are increments. We just happen to use the same notation. I don't know why they chose to use the same notation, but we do. We call this quantity is called the total differential. Of our function. And the total differential, again, just represents the change in height of the tangent plane as we move from one point to the other. So a couple of important things about the total differential. At a particular point, if we evaluate this at a particular point, the total differential is a linear function of delta x and delta y. These dz dx and dz dy are just our coefficients. We just get at a particular point, these are just numbers. So we get a linear function of delta x and delta y. So we can use this total differential as a linear approximation to the surface, to the increment at a particular point, just like we use the differential as a linear approximation in single variable calculus. So this lets us approximate the change in our surface with a linear function. Linear function is much easier to deal with than many other types of functions that we would have to work with. And then as our increments get smaller, delta x and delta y get smaller and smaller, our linear approximation is a closer and closer approximation to the change in the function from one point to the other. So we can approximate this better and better as we make delta x and delta y smaller. And as our increments get smaller, then dz, our differential, is approximately equal to our delta z, the increment. So we're using this as an approximating, as a tool to approximate. So what we're saying here is that as delta x and delta y get smaller, we can say that f of x plus delta x, comma y plus delta y, minus f of xy is approximately equal to, as long as our increments are small, to approximately equal to our total differential. And we can approximate this point if we add f of xy to both sides. We can say that our function value at x plus delta x, y plus delta y, is approximately equal to our function value at xy plus the total differential. So we can approximate the change. We can approximate our function value by using the total differential to approximate that change in the height of our tangent plane, or as the change in the height of our tangent plane, where you're going to use that to approximate the change in the height of the surface. So that's one place that we use a total differential. Use a total differential as an approximation, as a way to approximate our surface. We can approximate the change. We can also use a total differential to calculate error. So if delta x and delta y represent an error in measurement of a particular value, we can use a total differential to figure out how much the quantity might change due to that error. And we'll do some examples that have to do with that. So total differential, approximation to our surface. We're using the tangent plane to approximate our surface, and we can use a total differential if our increment is small enough it's approximately equal to what the surface does as we move from those 2 points. So any questions about the concept of the total differential? Okay, what I want to do is a couple of examples of how we use the total differential as an approximation and with error calculations. And then I want to bring the total differential into our idea that we talked about at the end of the class yesterday about differentiability. And we found out yesterday that multivariable functions behave a little differently than single variable functions. They can be that the derivative can exist where the function is not continuous. So we needed a better definition of differentiability than the existence of the derivative. And the total differential is how we do that. So I want to bring that back in at the end. All right. So for this example, we want to find our function and then use the total differential to approximate the quantity. So here's our quantity. 2.03 squared, 1 plus 8.9 to the third, minus 2 squared times 1 plus 9 to the third. So we want to find a function to represent that this could be representing, and then we want to use a total differential to approximate this quantity. So yeah, we could plug it into our calculator, but we want to relate this to the total differential. So let's write down the total differential. We know that the increment delta z, if we're thinking of this as a function, delta z is f of x plus delta x, y plus delta y, minus f of xy. So we're trying to picture this as being some kind of function in this form. So we're going to compare the forms of these two things. So here we have minus this quantity. So I'm going to say f of xy. I'm going to say this is my quantity f of xy. 2 squared times 1 plus 9 cubed. So what function could we say, how could we write a function of x and y? And we're looking at what is changing here. So this 9 is changing to 8.9 and the 2 is changing to 2.03. So how could we write this as a function of x and y? What function does this suggest? What are we doing to this quantity out here? Squaring it. So couldn't we say x squared? And we have a 1 here in both pieces for the y and the y plus delta y. So I'm going to say 1 plus y cubed. X equals 2 and y equals 9. So that would be my function f of x, y. And then delta x from here to, as I move from here to here, delta x is going to be what? 0.03. Delta y is going to be negative 0.1. So there's my function. There's my original point. There's my delta x and delta y. So now we can use a total differential to approximate this thing. So df dx, we need df dx for our total differential. We found our function. Df dx is 2x times 1 plus y to the third. Df dy. See, isn't doing calculus much more fun than using our calculator? Df dy is 3x squared. Well, I like calculators too, but calculus is way better. Times 1 plus y squared. So at our point, now we can plug in at 2, 9. Our total differential is 4 times 10 to the third times 0.03 plus 3 times 2 squared times 10, 10 squared times negative 0.1. So this is df dx, dx, and df dy, dy. And when I calculate this all out, this is 120 minus 120. This comes out to 0. So the approximate change in the function is 0. So this function changes approximately none at all in that change in x and y. Isn't that nice? All right, so one kind of contrived example of how we can use the total differential. All right, questions there. All right, let's do a little nicer example. We're going to talk about error in measurement. So we have a right circular cylinder. And our radius and our height are measured with possible errors. Of 4% and 2%. So we were better at measuring the height than we were at measuring the radius. We want to approximate the possible relative error in measuring the volume. So we're talking about the relative error. Relative error, did anyone help me out by telling me what we mean by relative error? You want to know what relative error means. Relative error means the error over the actual. So relative error, we want to find our error and we want to divide that by our actual measurement. That's what we mean by relative error. Well, the volume is a function of the radius and the height. We know that the volume of a right circular cylinder, hopefully, is 2 pi r squared h. The volume is a function of the radius and height. The volume is a multivariable function. So we're going to use our total differential to figure out the possible error in measuring the volume. So I'm going to say dV, our change in volume, is going to be dV dr, dr plus dV dH, dH. And these 4% and 2% errors in the measuring of the radius and the height, those are relative errors. So dr over r is 0.04. That's what we mean by a 4% error. The change, our error in measuring the radius divided by the actual radius is 0.04, and dH over h is 0.02. So we're going to use these quantities and our total differential to approximate dV over V. So our relative error is going to be dV over V. So let's calculate out dV, find our derivatives. So our total differential is going to be dV dr. So we get 4 pi r h dr plus dV dH, 2 pi r squared dH. And our relative error is dV over V. So that's this quantity, 4 pi r h dr over the actual volume, 2 pi r squared h plus 2 pi r squared dH over the volume, 2 pi r squared h. That's our relative error. And let's see. Okay, so we're good. So we can simplify this. So our relative error, when I simplify this out, I am left with 2dr over r plus dH over h. We have dr over r, that's our relative error in measuring the radius, and we have dH over h, that's our relative error in measuring the height. So our relative error in measuring the volume is going to be 2 times 0.04 plus 0.02, and we get 0.10 or 10%. So if we measure the radius and the height with relative errors of 4% and 2%, our relative error in the volume measurement would be about 10%. So relative error is the error divided by the total measurement. If the problem had given us something like measurement of, with a possible error measurement of plus or minus 0.4 whatever centimeters and plus or minus 0.2 centimeters, we could do our calculation and we'd end up with a range of values, a plus or a minus for our dr and a plus or a minus for our dh, and then we would get what we call the propagated error. The propagated error is when we include the plus and the minus for our measurements in the air. So if it said, for example, the right circular cylinder, we measured the radius at 10 centimeters and the height at 20 centimeters, and the error in our measurement was plus or minus 0.1 centimeters. Find the propagated error. Then our dr and dh would be plus or minus 0.1, and we could calculate the propagated error. The propagated error gives us a range of values. So in your homework, you'll have a question or two that ask you about the relative error and a question or two that ask you about the propagated error. Propagated error is when we could include the plus or minus in our dr or dh in our increments, and we carry that plus or minus through to our end calculation. So relative error is the error over the actual measurement. Propagated error is when we carry the plus or minus measurements through our entire calculation. So a nicer example of how we can use the total differential as an approximation for error measurements, approximating error. So questions on that example? All right. I want to bring this back to the idea of the total differential, back to the idea of differentiability, just briefly. So we had an example yesterday of a function that was not continuous at a point, but the partial derivatives existed at a point. So we said we needed a stronger definition of differentiability than the existence of the derivative. That's what for a single variable function, we said a function is differentiable if the derivative exists at a point. Well, we can have for a multivariable function, we can have the derivative exist where the function's not continuous. So that kind of doesn't work. So we use the idea of increments to define differentiability of a multivariable function. So if we have z equals f of xy, we're going to say this is differentiable. Our definition of differentiability if we can write our increment, guys, if delta z can be written as delta z equals df dx delta x plus df dy delta y plus epsilon 1 delta x plus epsilon 2 delta y, where our epsilons approach 0 as delta x and delta y approach 0. So this is our definition of differentiability of a multivariable function. If we can write the increment in this form where these epsilons approach 0 as delta x and delta y approach 0. So what that's saying is, essentially, is that our tangent plane as delta x and delta y approach 0 is a closer and closer approximation to our surface. So our surface, that tells us that our surface is behaving nicely at that particular point. If our tangent plane doesn't get to be a closer and closer approximation, then our surface, our function is behaving strangely at that particular point, and then our function might not be differentiable there. So this would take care of the function that we talked about yesterday at the point 0, 0. So this avoids the place where a function is not continuous but the derivatives exist. So if we're working with nice functions, I'm going to put that in parentheses, for nice functions, if our partials are continuous, then our function is continuous, or then our function is differentiable. So for well-behaved functions, this is enough of a condition for differentiability. If our first partials are continuous, then our function is going to be differentiable. Also, it's also interesting to say that to know that if f is differentiable at a point, then it is continuous at a point. So if this holds true at a particular point, then it is going to also be continuous at that particular point. So contrast that with what we had yesterday where the derivative existed, but the function was not continuous. So the existence of the derivative is not enough to say that the function is differentiable at a point. So multivariable functions behave a little differently. And this is how we define differentiability for a multivariable function. So that's how we get around that strange behavior. It has to do with the differential, the differential. All right, questions? Okay, homework. All right, there you go.